We're now going to continue our derivation of cubic splines, and in particular we're now going to look at how we can first of all make the system complete. Remember, before we only had n-2 equations but n unknowns, and we do this by implementing boundary conditions. So we need one boundary condition in order to help us calculate C1, and one for this imaginary variable Cn that we had to create in the process of deriving our equation. So as I mentioned last time, there's a number of choices. We are only going to consider natural and clamped conditions, and you can have a look at the textbook to look at the other conditions. So let's start off by looking at natural boundary conditions. These are the easiest ones to implement. Natural conditions are that the second derivative of our splines are equal to 0 at the endpoint. So let's have a look first of all at the left-hand side. So at the left-hand side, our spline is the first spline, f1, and its second derivative is given by that expression there. And if we substitute x is equal to x1 into this, and we enforce that the second derivative of x1 equals 0, this automatically gives us that C1 is equal to 0 from this term here, and that one drops out. So C1 equals 0 is a new equation, and indeed that's what we can add as an extra equation on the first row of the matrix, and that now means we have n-1 equations. Now let's look at the right-hand boundary. So the spline that goes up to the right-hand boundary is fn-1, and its second derivative is given by that expression there. And if we substitute that f double dashed at xn is equal to 0, so we just need to substitute x here is equal to xn, that then gives us that cn-1 plus 3dn-1 times hn-1 is equal to 0. Unfortunately, we can't use this expression here directly as an equation because we don't yet know what dn-1 is equal to. However, continuity of our spline at the node point suggests that if we defined an extra spline that went from point n to point n plus 1, even though there isn't a point n plus 1, that the second derivative of that equation would be equal to Cn. Therefore, this thing that we've calculated here is equal to Cn. Thus, Cn is equal to 0. So we've already added our dummy variable Cn into our system previously, but Cn equals 0 actually is the appropriate boundary condition for natural conditions on the spline. So now we've added our nth equation, we have all the equations we need, and we can write our tridiagonal system like this. So the very first equation, which we figured out was C1 is equal to 0, is just given by this first row of the matrix, multiplied by that column vector, so we have a 1 times C1 is equal to 0. Likewise, the last row of the matrix is equal to 1 times Cn is equal to 0. And the rest of the equations are just in the normal tridiagonal form, where the right-hand side values across here are given by this expression here. Okay, this is an n by n system. Now, it would be possible also to explicitly use C1 equals 0 and Cn equals 0 and reduce our matrix problem to be an n-2 times n-2 system. So in other words, you delete the first column, the last column, the first row, and the last row, and you'd end up with a system of equations that looked like this, which is a perfectly good tridiagonal system. Again, the right-hand side will be equal to the same thing as before. Whilst you can do this, there are certain advantages to keeping the system as an n by n system, in case, for example, you want to make your algorithm generic. In other words, it will handle clamped conditions, it will handle natural conditions, or a mix of both. But you can do it either way. Okay, so that's how we deal with natural conditions. Now let's have a look at clamped boundary conditions. So, Clamped conditions are that the first derivative of the spline is equal to a given value. And let's imagine that we want the first derivative of the spline at x1 to be equal to s1, so it's a slope that we want to specify, and that the first derivative of the spline at the right-hand side at xn is equal to some different value. Let's call that Sn. Those are the two things that we're trying to satisfy. So let's look at our expression for the first derivative of the first spline, f1 dashed. It's given by this expression here. We've derived this previously. And if we set x is equal to x1, in this expression here, we just get that f dashed of x1 is equal to b1, but we've defined f dashed of x1 as being equal to s1. So we know that b1 is equal to s1. So if we use equation 6 that we derived previously, this gives us, if we keep the move the c values to the left-hand side, that twice c1 plus c2 times h1 is given by 3y2 minus y1 divided by h1 minus 3s1. Okay, so we've now got an equation where we have unknown values of c on the left-hand side, unknown values of y, and our slope on the right-hand side. So this is then the equation that we can use for I is equal to 1. So this is now one of the extra two equations that we need. We need to do a similar thing at the right-hand side. So the first derivative of our spline, it's got to be the n minus 1th spline, at the right-hand side, what's the derivative is given by this expression here. If we substitute x is equal to xn, we end up with bn minus 1 is equal to this expression here. That's just by the fact that we're using this condition here. So, equation 4, that's this equation here that we derived previously, at I is equal to n minus 1, gives us that dn minus 1 is given by this expression. So we can then substitute that into equation 14. That then gives us, so after a little bit of algebra, bn minus 1 is given by this. We then substitute equation 15 back into equation 6 with I is equal to n minus 1. So just replace I is equal to n minus 1 in this expression here. Then after we do a little bit of algebra, and it's a slightly complex, this one here, we find the following expression. An expression that rates Cn minus 1 and Cn to values of y and the slope that we want to use as the boundary condition at the right-hand side. And so this equation here, equation 16, is the equation that we use for I is equal to n. So, if we take equation 13 from the previous slide and equation 16 from this slide here, and we put these into the matrix, we end up with the following tridiagonal system. So it looks pretty similar to before. This now is an n by n system. The right-hand sides on the interior points are the same, however the right-hand side at the boundary condition look different, but we've now got the unknown C1 through to Cn. So we've got a tridiagonal system that we can use the Thomas algorithm to solve for. This will then give us the unknown values of the CI. Once we have those, we calculate di from equation 4, just given by this expression here. We calculate the bi from equation 6. And remember, we had already found that ai was equal to yi. So we now have all of the coefficients of our spline. Everything we need to detail how to implement or how to calculate the splines. The only tricky thing from here on in is if we want to use the spline to calculate the value at a certain value of x, we need to figure out which of the n-1 splines we need to use. And that's something that we'll probably look at in computer labs.